Increasingly, I realized in over nearly 10 years of doing this, most of modern science is so siloed, so narrow, that people rarely get the chance to look at the big picture. And so I kind of became a big picture person. And I realized that the result of this siloing in these subjects, especially biology, meant that people were working on fantastic things. You know, the movement of electrons in mitochondria from one place to another in intricate detail. Wonderful stuff, but nobody saw the big picture. And it turns out the activation energy, which has been determined by biologists over all life forms from bacteria to the blue whale, is around 0.7 electron volts. Almost exactly the same as the peak photon flux coming from the sun. I thought, that's not an accident. The structures that you have to maintain your homeostasis are tuned to an energy source which can allow you to overcome these barriers, but in a controlled manner. Well, there's a word for this. It's called hormesis. You have to stress yourself in order to remain healthy. You give yourself small doses of stress, like toxic chemicals and so on. You need to get your body to react to difficulty. It forces you to build the complexity.
Welcome to Sunlight Matters, the podcast that reconnects us with the sun. Join us as we explore the power and influence of our star, the force at the heart of everything. Each episode, we speak with leading experts to uncover the ways sunlight shapes our world.
Welcome to today's episode of Sunlight Matters. Joining Georg and I is an incredible person, Bob Fosbury. So welcome to the show, Bob. I wonder, could you do a brief introduction to yourself? And then, let's get on with talking about some of the big themes that we want to talk to you about.
Okay, right. I'm interested in interdisciplinarity. I mean, I'm an astrophysicist. I worked for 50 years on an astronomical career. I'm still doing it, actually. I'm still doing it in the background. But so I grew up in British astronomy initially through the Royal Greenwich Observatory, where I did my DPhil at Sussex. Then I went to Australia to work on the Anglo-Australian telescope. And then I worked a bit on the La Palma telescopes. And then I received a phone call inviting me to join the European Space Agency to work on the Hubble Space Telescope program, which I started doing in 1985, 5 years before launch. And I worked on that program for, I think, 26 years.
Wow.
Both as an astrophysicist working with data and so on. And but I was hosted by the European Southern Observatory in Munich, in Germany. And so I lived there for a very long time. And I had a very, very exciting astronomical career using the major telescopes around the world, Hawaii, Chile, and so on. I was involved with many projects. I was chairman of the ESO faculty, which was the largest faculty of astronomers, I think, in the world at the time, 80 PhD astronomers and so on. So I had a sort of mixed academic and operational role in helping ESA with their collaboration with NASA on Hubble, and also a little bit on the development of the James Webb Space Telescope. I was involved in a relatively small way with the early development of the instrumentation for the James Webb Space Telescope. When I retired from ESA in the end of 2010, I didn't really want to follow many of my colleagues who, when they retired, just continued doing astronomy, just continued doing exactly what they were doing before, but not being paid for it. And I accidentally came in contact with Glenn Jeffrey. I mean, completely accidentally, when I was in Durham on a fellowship. And we worked on reindeer vision, which turned out to be very interesting, and all to do with photonics, photonic crystals in life and so on. And his main project at the time was working on the effect of infrared light on vision and slowing macular degeneration by making sure that the eye was bathed in infrared light occasionally. And well, I won't go into the details of that, but basically I got very interested in this whole question of the interaction of light with biology, and realized that there's not very much known, and increasingly, I realized in over nearly 10 years of doing this, most of modern science is so siloed, so narrow, that people rarely get the chance to look at the big picture. And so I kind of became a big picture person. And I was in a great position to do that because, of course, I spent my whole career doing astronomy. I published papers in the Journal of Solar Physics and also published papers on the edge of the universe and the properties of black holes and so on. So I had this enormous perspective just by virtue of where I was and what I was doing. And, I'm not trained in chemistry or biology to any significant level, but, I was trained in physics. And I realized that the result of this siloing in these subjects, especially biology, meant that people were working on fantastic things. The movement of electrons in mitochondria from one place to another in intricate detail, wonderful stuff. But nobody saw the big picture. And then when I came across this, I found the early literature on this topic of scaling factors in biology, and I looked at the original papers, and I thought, golly, this is really important stuff. And of course, Jeffrey West, who wrote this book, was a particle physicist. He was trained in high energy physics. He was involved with the development of the detectors for what was going to become the superconducting super collider. So he was working at Los Alamos. He was head of one of the detector teams on for Hadron for the collider. And when he, kind of lost his job because they cancelled the collider, he moved into biology because he wanted to understand death. What determines your lifespan? And this is how he got into the scaling law. And the scaling law that came out was absolutely he didn't discover the scaling law. It was actually discovered by Kleiber in the 30s. And but they figured it out. He and James Brown and a student, Enquist, they sorted all this out in the late 90s and early 2000s. And it was revolutionary for biology. But it seems to me that most biologists didn't notice this. And it's incredibly important for ecology and how animals work in different environments and so on. So, what I've been doing over the last year or so is trying to understand this interface between the mathematical biology, the scaling laws between different properties of life, and what that implied for the energy flow into biology. So what we're doing is bioenergetics. Biology has been dominated by genetics for the last 50 years. And, there's some people working on bioenergetics. Nick Lane is one of them, very well known. But the energetics of life is absolutely crucial. And it just turns out, and this has only happened to me over the last few months, I must say, the last few months have been just an amazing intellectual storm for me to suddenly realize that all these big pieces of jigsaw that we were jostling around trying to fit together, suddenly they all came together. And it was an extraordinary experience. And I did one plot just a few weeks ago when I was on holiday, and I plotted 2 points on a diagram, and I thought, gosh, that's what we're talking about. The whole process of metabolism is to do with sunlight. And of course, we know sunlight is crucial for photosynthesis. We've known this for a long time. It's only recently it's really been understood at sort of quantum mechanical level, and not completely understood yet, I'm sure. But photosynthesis is crucial because it basically drives life on Earth. I mean, not all life, completely all life, but pretty much everything we know about is driven by photosynthesis. And then we gradually realized that there was a parallel process going on to photosynthesis, which was its inverse. You produce the food, but then how do you metabolize the food to drive your cells? How do you create ATP, this currency that cells use to energize themselves? How do you generate ATP? And the reason we made these discoveries, and I think this is very important, is that what we did in lighting over the last 50 years, all life on Earth has evolved under thermal light sources, i.e. things that radiate because they're hot. Sunlight is a perfect example. Sunlight is the obvious. But, you think of all the other ways life has interacted with light. Fires, in the early days of human civilization, candles, oil lamps, they're all thermal sources of radiation. And that thermal sources of radiation have a very broad spectrum. And at this time, we were getting fussed about using energy. And so we were trying to design very clever light bulbs that only produce visible light. And so we could save energy. And the fluorescent tube, obviously and these compact fluorescent tubes and so on, they were all doing this. There was very little broad spectrum light. Most of the light comes out in the visible. And then this wonderful idea of the blue LED, which would excite phosphors to make white LED lights, got the Nobel Prize. For goodness sake. Fantastic idea. Now we can light the world. And so for the last decade or so, we've been lighting the world with this wonderfully efficient LED light, which is killing us. And I'm not being, I'm not exaggerating about this. White light on its own, white LED light, we now have the evidence. Glenn and people are working on a paper about this. It's not only not good for us, but it actually damages. It damages mitochondrial function. And so, if we live in the built environment now, which most people do for most of the time, they're sitting in a building that has white LED lights. There's one of them here on my desk. Actually, this light is a 60-watt tungsten filament lamp dimmed with a dimmer, and that keeps me alive. And this one allows me to see.
Well,
so they dual function, okay? But
it's amazing. It's amazing.
But it's so obvious in retrospect. And what they're doing in buildings now, and they have to do this, if you build a skyscraper, you have to reject the infrared. Otherwise, your skyscraper would fry everybody because of, thermal imbalance and so on. So the glass manufacturers are proudly making glass now that only emits visible light into buildings. And the combination of that and the white LEDs mean if you're somebody in Saudi Arabia living in a skyscraper and you've got plenty of money, you never go into sunlight. You go from your skyscraper to your air-conditioned car with infrared rejecting windows and LED lights. So you're living entirely under LED lights, which is what the astronauts in the space station do. And I think, and the Gaia Foundation has written a report to the space agencies about this, the reason astronauts come back sick from the space station is at least partly, and I think predominantly, because they're living under white LED lights and they never get infrared light.
So
they can't open the windows.
If Elon wants to go to Mars, he definitely needs a few incandescent lights in the spaceship. Bob,
but he can figure that out.
Yeah, well, absolutely. But Bob, I mean, utterly amazing. I think the fact that you've gone from astrophysics into biology and you've kind of done the silo busting along the way, and you're starting to figure all of this stuff out, I think is incredible. And I think that was it was a tremendous introduction. And it kind of sets the scene. But I think one of the things I was keen to do was for you to replay a bit of the presentation that you did the other day, which was about the origins of the universe. So taking you back to Hubble and the James Webb experience that you had, where you peered back in time. And I think the reason it's important is because it sets the scene for life today. Like, without what happened in the Big Bang, and from what you said, without what happened in the Big Bang and the subsequent steps that happened along the way, we couldn't be where we are doing what we're doing. And so I was keen for you to do that. And then I was also keen to spend a bit of time demystifying the sun, because the sun is, like, for us, is the kind of main the main giver of life in terms of many things. But I guess a lot of people don't really understand what's going on in the sun, how big it is. So some of the fundamentals as well. So
Sun
if
is
we,
our boss, so it's really crucial here.
yeah. So if we could start by going through that sort of a brief history of time, that would be brilliant.
Yeah. Okay. Well, in fact, I wrote an essay on the life, universe, and everything seen in colour for the Bath Royal Literary and Scientific Institution, and I gave that lecture in 2017, and it's on Flickr, the website Flickr, and actually it's my most popular Flickr post. It's a photographic website, but I've got about 10 pages of text in there. And it's been viewed, I think, 25,000 times now, which is for Flickr is quite a large number. So I can send you that essay, and that covers my view of that, some years ago now. So it doesn't include any of the more recent stuff, but it certainly includes the idea of the big picture of what's going on in the universe. But what I did in the talk, I started off with the idea of showing what the history of the universe in the way that I showed it on a sort of logarithmic time scale, right from the very beginning. And the first event that we can see clearly now is the cosmic microwave background, which happened about 380,000 years after the Big Bang. This is known quite precisely from the studies of the background itself. And that was the moment when the Big Bang fireball, if you like to call it that, became transparent, and huge numbers of photons were set free to flow through outer space. And they're still the dominant the dominant source of photons in the universe at the moment by a large factor. It's the cosmic microwave background. Now, the thing is, when that started, when those photons were emitted, they were emitted at a much higher temperature than they are now, because the universe has expanded by a factor of 1,000 or more than 1,000 since then. So the photons emitted were a perfect black body at 3,000 kelvins, which is the temperature of a hot tungsten filament lamp, incidentally, and that's a coincidence which I like to use. So, we're struggling to get back to to the first light in the universe in our rooms, and failing at the moment. Except I'm not failing. I've got one here, but this was the first light that was emitted into the universe, and the reason I included that in the talk was because we see that light all around us on the sky. It's all around the sky, and it's very, very uniform. It's almost exactly the same temperature all over the sky. The deviations from that 3,000 Kelvin black body are tiny. They're about 1 part in 100,000. And these are the maps you see from these satellites. I'm sure you've seen the Planck map of the all-sky Planck map, which is this mottled red and blue structure. Those fluctuations represented by the red and blue are tiny.
Mm-hmm.
The 1 part in, I say, a few parts in 100,000. But they were absolutely crucial because they were the inhomogeneities in the universe which allowed gravity to collapse it in a non-uniform way. I mean, so this is what
Otherwise, there would just be a gas cloud, right? There would be no.
It was just a huge gas cloud, but slightly inhomogeneous. And of course, gravity acting on that will collapse the denser parts quicker than the less dense parts. And so this is what started to form the structure in the universe. And after a couple of 100 million years, not a very long time, this formed the first stars. And this is what we're trying to see with the James Webb Space Telescope at the moment. That was one of its goals, was to see the first stars.
Can I ask a quick question, right?
Yeah.
At this point, I think it makes sense. When we think about this cosmic dust initially that then eventually formed stars, did this at the same time form planets, or did the planets emerge from prior star structures?
That's an interesting question to address. I mean, of course, the material that was collapsing at that time was essentially pure hydrogen and helium, because those were the only two elements that were formed in the Big Bang process
This is
itself.
not really a planet consists of, right?
So you couldn't form a planet at that time. No, there's no way of forming a planet at that time. But the point was that hydrogen and helium was formed by during the cooling of the universe, and this was a time which was between 1 and 2 minutes in the history of the universe. It was a very short time, of just a couple of minutes in the history of the universe, when the kinetic temperature was high enough to actually fuse hydrogen into helium. And so there wasn't enough time. Then it cooled too much, and there wasn't enough time. And people thought originally that all the elements were forged in the Big Bang, but that's not true. And George Gamow actually was studying this at the time in the 40s, and realized that there wasn't enough time to form all the chemical elements. So the first stars had to form out of hydrogen and helium only, a little bit of lithium perhaps. But it's quite hard to form a star without the heavier elements, because the heavier elements allow the stars to cool as they collapse. You know, the bicycle pump effect. As you collapse a star, it gets hotter and hotter and hotter. And eventually it gets hot enough in the core to trigger nuclear fusion, which generates the energy, which eventually radiates as starlight. So there's a process here where you have to cool the star without the heavy elements, and it's difficult and slow. And the consequence of that was, it seems that most of the stars, or perhaps all the stars that formed first of all, were very, very massive and very, very bright, and emitted almost all of their energy in the ultraviolet, very little in the visible. It was all in the far ultraviolet, because the stars were so hot. Instead of being 6,000 kelvins like the sun, they were 100,000 kelvins. So they're really, really hot.
So that's what the James Webb telescope is trying to find, these stars, is it?
It's trying to find these stars, and I think that we probably won't see them directly. It's very hard to see them directly, because at that time the universe was neutral. The hydrogen had electrons with it, and that was opaque to ultraviolet radiation. So all these forming stars were being shrouded in a mist, which we can't see through. But there's a peculiar process that goes on here, which allows us to see these photons coming from these early stars one step removed from their emission. They're radiated by the photosphere of these very hot stars, but we can't see them directly because the intervening universe is opaque. And most of those photons will interact with the hydrogen atoms in the surrounding medium, and they will scatter off the hydrogen atoms. So it means that most of the light that's coming out of the stars ends up as the fundamental line in the hydrogen atom from the first excited level to the ground state. And that line is called Lyman alpha, after the guy who discovered the Lyman series. You maybe have heard of the Balmer series of hydrogen lines in the visible spectrum. Well, the Lyman series of hydrogen lines is in the ultraviolet. So all these Lyman alpha photons, they bounce around and they eventually escape. They maybe bounce thousands of times before they get out of the mist. And then we see them, and we see Lyman alpha emission around these forming stars. But actually, they can't, they can get out more quickly. And they do this by exciting the hydrogen atom up to the first excited state. And there is a way that hydrogen atom in one of its forms of the first excited state, the most common form, cannot transition back to the ground state because of a quantum mechanical selection rule. So you're going from a singlet state of hydrogen to another singlet state of hydrogen, and it doesn't work. But very occasionally, you can break the rules of quantum mechanics, and that excited hydrogen atom can decay by emitting 2 photons instead of 1. And it's called 2-photon emission, and we can observe that with telescopes, the James Webb. We observe that with the telescope now, and we see that light coming out, and that's probably light that was emitted by the very, very young stars, which we may never see directly, but it's the most direct method we have of seeing the light coming from the first stars. And we can see that very clearly with the James Webb now, and we can characterize it and
And the
understand how
telescope
it
can
works.
differentiate between those like who emit 2 photons versus those who just emit a single photon. That's possible.
Yeah. It's it's a well-known process which was discovered in the 20s, I think, 1920s. It is it's one of these many ways in which the strict quantum mechanical selection rules don't always work strictly, because you can get around them in other ways. And by emitting 2 photons, and these 2 photons, the sum of energies of these 2 photons is exactly the same as the energy that the single photon would have if it were able to escape. Anyway, that's a bit of a detail, but it's quite an interesting thing, and it brings us to the whole question of the origin of the first stars and how they start populating the periodic table. And they will start doing this very, very quickly, because these stars are so luminous that they run out of life. They run out of their nuclear fuel in perhaps just a few million years, not 10 billion years like the sun. It happens very quickly. So these stars go off like flashbulbs in the early universe. And when they explode as supernovae at the end of their lives, they distribute their fusion products into the surrounding medium. And this goes into the formation of the next generation of stars. So gradually you build up the abundance of the heavier elements as you cycle through generations of stars through the history of the universe. And of course, there are many generations of stars going on now. And so this is
Stars in the future, like in the very distant future, who are very different than our current stars, like the process.
If you're enjoying Sunlight Matters, make sure to subscribe and leave us a review on your favourite podcast platform. You can also search Sunlight Matters on Google to find more episodes, guest information, and further insights about sunlight analysis, solar exposure, and the way light shapes our spaces.
Well, the universe will end up with everything being iron, because it's the most stable element. But that'll take a very, very long time. But the point about the generation of stars, it happened very quickly in the early universe. So these stars mostly live very short times. So there were many cycles per unit time in the early universe. And so very quickly, the abundance of the heavier elements, carbon, nitrogen, oxygen, silicon, magnesium, iron, all those things, the elements heavier than iron are different, slightly different story, but all part of the same process, but a slightly different story. So even the very earliest stars that we see, if they're not absolutely the first generation of stars, those early stars will contain these common elements: oxygen, carbon, nitrogen, magnesium, and so on, neon. We see these, all the spectra of the early stars we observe with the James Webb Space Telescope, and could indeed do with Hubble. They contain these elements. They may be only at 1% of the level they are in our current universe, but they're easy to see, so we can see them. So we can map the development of the periodic table by looking at the spectra of these very early stars, or at least the nebulae around them. And so what happens is that these stars are, going through their generations, they're emitting lots and lots of starlight, and the amount of starlight they emit is intimately associated with the abundance of the elements they're producing. So it takes nuclear fusion to produce the periodic table, and it's the same nuclear fusion that generates the starlight. So there's essentially a one-to-one correspondence between the growth of the amount of starlight in the universe and the growth in the abundance of the elements. And I showed this cartoon, which actually showed these lines overlapping. I mean, it's meaningless in the way that they overlap, but they develop in concert with one another. And of course, the starlight is what allows these stars to remain stable while they're burning nuclear fuel. Because if they just burn nuclear fuel and they couldn't get rid of all this energy they were producing, they would blow up. And so it's the starlight which migrates from the core, where the temperatures are very high, millions and millions of degrees. These photons, they transition through the whole body of the star, and eventually reach the surface. They don't reach the surface as the same photons, because obviously right in the middle, they're gamma ray photons. They're very energetic. But as their energy seeps through the star to reach the surface and get radiated, you get lower and lower energy electrons, photons, sorry. And so the photons that are radiated from the surface of the star are the waste energy from the nuclear fusion in the core. So, and this is where I try and introduce the concept of entropy, because entropy is basically the waste energy that you have to produce if you organize anything.
Mm-hmm.
And you have to organize your bodies into what we call homeostasis in order to keep yourselves alive. And the energy you use to build that order in your body is the energy that you ingest from food. In a star, it's the energy you get from nuclear fusion in the core, but in your body, it's the food that you eat. And most of the food that you eat generates waste heat. So if you eat 2,000 calories a day, you'll generate about 90 watts of waste heat. And only about 5% of that will be used as useful energy to allow you to think and move around and so on. So most of the food you eat ends up as waste heat, which you have to get rid of by sweating or radiating or whatever, lying on a cold sheet of metal or something, whatever, to take your waste entropy away. And this is when I realized, and other people have realized this as well, but the close analogy between the basic energetics of a star and the basic energetics of a living being, anything in the biosphere. And that is you need a source of energy. In a star, that's nuclear fusion. In a life form, it's the food that you eat. In the sun, in photosynthesis, of course, plants have to generate their bodies, and they do this in their mitochondria in the way that animals do. So they have an animal component in them as well, but they produce the food as well in plants by photosynthesis. But if you have a star, you have energy coming in, you have starlight going out as your waste product. Now, for a life form, that starlight is actually a highly ordered nutrient for you. It's a very powerful nutrient, and the products of photosynthesis attest to that. And we're arguing that we need to absorb this starlight as well to metabolize our food, not only to generate it in plants, but also to metabolize it in animals and fungi and so on. So there's a very close analogy between the energy flow through a star. It's producing waste heat, which we call waste entropy, which I'll explain a bit in a moment. But and in a body, in your body, you're ingesting food, which is allowing you to maintain the order in your body, which allows you to live. If you didn't have that order, you come into thermodynamic equilibrium with your surroundings, which would mean you were dead.
Mm.
So you eat in order to maintain your order inside your body. And this was Schrodinger's famous statement: you eat order in order to maintain the order in your body. This is why you need highly ordered foods. And incidentally, and I'm not going down this route, incidentally, ultra-processed foods have no order.
Low order.
They have very low order. No, they have very high order. They have
Right.
they're completely disordered. Sorry, they have very low state of
Order.
Yeah, and this is the common confusion we get with talking about entropy.
Mm.
Schrodinger introduced the concept of negative entropy, which means highly ordered. Lots of entropy means you're completely disordered.
Yeah. No, that's which is. I mean, I presume, like, I picked a couple of apples off my tree this morning. I presume an apple is a very highly ordered thing.
Yes, exactly. Structure. The structure is very important. The cellular structure, the fact that it contains things like amino acids. An ultra-processed food doesn't contain anything that's structured. It's just pure chemicals. So we call it maximum entropy food. You couldn't make it more useless as food if you tried.
And isn't it like that these like very natural foods are just carrier of starlight and you ingest it and then you bring
Yeah,
that of that
they're
light?
yes, they're carriers of order.
Mhm,
And the sugars you produce are highly ordered because they're very energy rich.
mhm.
With
So they're highly ordered foodstuffs. So
I mean, very, very interesting. I mean, the other point that you made in your presentation was about the cooling universe and how you know the reality is we need that cool universe in order to get rid of the heat.
exactly, yes. I mean, that's really the point of me showing this cosmic microwave background, because at the moment, the cosmic microwave background has moved from being 3000 kelvins to being 2.75 kelvins. So it's very cold. And that coldness surrounding us is absolutely crucial, because if we didn't have that cold surface or volume to radiate into, we couldn't use energy to create order in our lives, because there would be no way to get rid of the waste heat. And incidentally, this is a good way of introducing the idea of being inside. Now, we're all sitting in a room where I guess the temperature of the walls is around 20, 21, 22 centigrade. And the energy of our bodies, internal energy of our bodies, internal temperature of our bodies is 37 degrees. So there's not a very big difference between the temperature of our surroundings and the temperature inside our bodies. And the result of that is that we can only ever produce, when we're in a room like this, about 5% of our ingested food energy. We can only ever produce about 5%, which is useful, which is what allows us to do stuff. The rest is waste heat we have to get rid of. And getting rid of waste heat from 37 degrees to 22 degrees is not very efficient. If our room was at 5 centigrade, we would probably be able to we would be able to generate about twice as much energy from our food than we can. And what happens if you walk outside if I walk outside now, I mean, some of the sky is blue. If I walk out under a blue sky and I point a radiative thermometer, I have one here, one of these radiative thermometers. If I point that at a clear blue sky in the zenith, it'll read -40 or -50 centigrade. So much, much colder than your surroundings in a room or on the ground, or normally on the ground. So this is why, one of the reasons why it's so important to get outside is to expose yourself to some part of your environment which is cold, because it gives you much more energy. And I think, in a way, you asked about going broad and deep. You know, all the development, the Industrial Revolution development happened at mid-latitudes. We know that happened in Britain, mid-latitudes. And think of these navvies that went to build the canals and to build the railways. They were eating something like 8,000 calories a day, and they were producing huge amounts of energy to shovel dirt uphill and so on, to build embankments and dig canals and so on. They would not have been able to do that in the tropics. You could not have had an industrial revolution like that in the tropics, because you could never have used people to produce enough energy to do that. So having cold surroundings is enormously beneficial. And I mean, I've noticed this absolutely viscerally. We've had a very hot summer, and, you know, when it's really hot, you go for a walk outside and you get exhausted. But, you know, over the last few days, when it's been quite cool outside, you bounce outside and you walk around and think, this is great. And this is pure thermodynamics. It's simply the Carnot cycle. You know, the efficiency of, you've muted yourself, Dave. The efficiency of generating energy in your body is dependent on the temperature difference with your surroundings. And
It's I mean, it is amazing to think. I mean, what one I mean, I'm bouncing here, but that what you see is that there is a definite order to, like, the way that the universe started,
yeah,
what then happened, and you can almost draw a straight line. And you've done this actually. You've
mm,
to life as well. There's a straight line. So we are, there was a map of order.
Mm.
Which immediately makes me think that, well, we can't then be the only things that have ended up like living. We can't be the only living things in the universe, because there's a straight line to all that we're part of this line. I mean, and sorry, it's just a very random thought that I had.
No, it's I'll focus that thought slightly and say, yes, in my opinion, the things we're talking about at the moment will be true of any, at least Earth-like planet which has carbon-based life on it. All of these scaling laws will be the same because they're related. They're so closely related to the properties of the star and the properties of the elements that form the periodic table. And so I think the picture we're painting at the moment would essentially apply to any planet in the universe which had biological life on it.
And so that biological life is probably going to be similar to biological life on Earth, because it's like it sort of feels like there's a map. There's a map there.
Well, this is the common scaling law, yes, which applies to all of life on the planet, and would apply to all life on any planet. I think it's physics. It's just physics. It's nothing to do with DNA and biology. So it's physics.
Look,
it's energy flow.
And I'm sorry, I just had that thought and was, bounced around on it. I really would like to go back and talk about our sun, though, because what how big is our, just some basics about the sun, like how does it compare to other suns out there?
Well,
it's obviously very special to us because
top 10 of best stars in the
closer. Well, I'd say it's top one of best stars in our solar system. So
our solar system, sure, yeah.
I mean, I saw Brian Cox did a brilliant program on the planets, but one of the things that really fascinated me was just the sheer scale of influence of the sun on the solar system. He basically he had to drive for kilometers. He sort of said, assume I take 2 steps and that's from a rock and that's the Earth. He then had to drive for almost kilometers before he said, this is the end of the impact of the sun on the solar system. So look, it was just, because we've got you here, be a good chance to get some basic facts on the sun.
Well, I won't do numerical facts because unless they're necessary, because people can easily look those up. Okay, but I'll paint the story. The thing is, when you form a star out of an interstellar medium, you have this chaotic molecular cloud around you, which contains molecules and atoms and so on, and it's floating around in interstellar space. And there will be some effect which triggers some part of that cloud to collapse into a star. And you often collapse stars into clusters because you collapse many stars more or less at the same time. And it's gravity, of course, that pulls these stars together and fragments them into individual stars. As the gas cloud collapses, there'll be some turbulence in the gas cloud. There'll be motions, flows and motions, small motions, but they'll be there. And as you collapse down to having what you would recognize as a forming star, a dense collapsing gas cloud, the motions, the random motions, will assert themselves as a net angular momentum. So the star will start to spin with a particular axis as it collapses, and like a ballet dancer spinning round, as it collapses, the spin speeds up because you have to conserve angular momentum. And the only way you can conserve angular momentum if you start off in the large scale and you're getting to a small scale is to rotate faster. And so all stars will end up with an excess of angular momentum, which is not able to fall into the star. It's got too much momentum. So it forms a disk. around, like Saturn's disk. It forms a disk around the star, and we call this a protoplanetary disk. And we see these now. We can image these. Hard to do with optical telescopes. Much easier to do with sub-millimeter telescopes working at longer wavelengths where the star is very dim, so you don't get this enormously bright light source in the middle. And I showed in my talk, I showed you a number of images of these protoplanetary disks. And those disks contain the less volatile elements. The hydrogen will probably escape as soon as it warms up a bit, but of course, you can collapse hydrogen into massive planets, but you can't collapse hydrogen onto the Earth because it's too small. We lose the gaseous hydrogen from our atmosphere very quickly. Anyway, so every star will have a protoplanetary disk in some form or another, and that's the material from which the planets are formed. And that material contains the whole spectrum of elements in the periodic table that were present in the molecular cloud, including the molecules that are formed in interstellar space. So this is stardust, which collapses into a planet. And you get fractionation there. You don't keep all the hydrogen, you keep very little of the helium, because the Earth is not big enough to have strong enough gravity to hold the atoms into the atoms are moving too fast. They move faster than escape velocity, so they escape. But we end up with the heavier elements on the planet, and they form the material from which you can generate the next scale of complexity, which is biological evolution. And so, one's now generating an analog of a star, but on the planet in the form of life. So life is developing out of this stardust using the elements, using the organic atoms that you need, carbon, nitrogen, oxygen, but also the other elements that are necessary for normal life, like some of the enzymes and so on. All of that is present on the planet. And you're organizing those elements into self-organizing chemical mixes, which, gradually develop into life. And so that life then operates on the same plan as the star. You have a source of energy, which is derived from sunlight. You have a source of material, which is the stardust from previous generations of stars. By this time, the universe is fairly rich in heavier elements because the bulk of the star formation happened about 10 billion years ago. And we're not producing nearly as many new stars now as the universe was at that time.
Right.
So, all the periodic table is very well populated now with elements for enabling life to form. And so then we develop life forms which have a source of energy, they have a source of materials, and they have a way of radiating their waste heat into outer space. And they can't do it because they're on the surface of the planet. They can't do it directly to the 3 kelvins of outer space. They have to go via the atmosphere. And there are windows in the atmosphere which are relatively transparent. They have very little absorption in them. And it's these windows that are used to radiate the excess waste heat from all of this complexity generation associated with life into outer space. And the main one of that is between 7 and 14 microns wavelength. And that's where these radiative thermometers work. Because 7 to 14 microns is where the black body radiation of the Earth is. So the Earth is radiating all the heat it gets from the sun. That energy is conserved somehow, and it's continuously raining on us from the sun. You have to get rid of that energy, otherwise your Earth is going to heat up. So you get rid of that mostly through this window between 7 and 14 microns, goes out into outer space and is lost, and enables the Earth to retain its temperature stability.
So what the micron wavelength you describe, what electromagnetic frequency are we talking here about? Is this like infrared, or what is it?
This is it's mid-infrared.
Okay.
Yeah, it's so it's no, I say it's the temperature. It's the window within which these thermometers and the thermal imaging cameras work in the same range. So, any thermal imaging camera will be looking at the radiation from the Earth and from you and me
hmm
at those wavelengths. And those wavelengths, obviously, it doesn't generate. We don't generate wavelengths in the visible. Well, actually, we do in the body. There are biophotons that are generated inside the body, but they're not very bright. They're very rare. But so we have to have a way of radiating our waste entropy into outer space, and this whole climate change stuff that we're talking about, it's a very inappropriate name for a phenomenon which is actually very basic. Climate change is a symptom of what's going on in the Earth at the moment. It's not the cause, it's a symptom. And what we're doing is we're closing this window a little bit,
hmm
the window through which the Earth radiates its excess heat, because one of the main absorptions in this window is carbon dioxide. And there are other absorbers, water, methane, and so on, in the window. So we're closing that window a little bit, and the Earth reacts by becoming hotter. It establishes a new equilibrium. In order to radiate its heat away, it gets hotter.
Seems like a super sensitive system. I have a question, because there are some thoughts of dimming Earth's atmosphere to let in less sunlight. Wouldn't that be kind of counterintuitive to what you're describing? Like, couldn't that also?
Well, I mean, that is a potential solution. You either find a way of getting rid of your waste heat better, or you stop so much heat coming down from the sun. So, yeah, if you reflect some sunlight, this is why you get global cooling after the meteor impact that destroyed the dinosaurs. You think it would get very hot. Well, it did get hot for a short period of time, but then it got really cold because the sunlight was being reflected from the top of this gas cloud, and this is what the nuclear winter is. It's you generate lots of stuff in the atmosphere which reflects light out, so it cools. So it's a complex interlinked system. It's a series of feedback loops, but what we're doing is stopping the Earth radiating all the energy that it's generating. And of course, you and I will only radiate 100 watts, call it 100 watts, 90 watts or whatever, depending on how much we eat, but we'll radiate 100 watts. Now, if you have a city with a transport system and infrastructure and air conditioning and heating and so on, and you share that, all the energy you're using to drive the functioning of the city, if you share that out amongst the people who live in the city, it means that you're radiating much more than 90 watts. I think in Jeffrey West's book, I think he says we in a big city will be responsible for something like 11 or 12 kilowatts of energy, which is way more than what we're radiating just as a biological system. And this is why, the planet that we have and we're building at the moment is unsustainable. It's demonstrably unsustainable because we're generating so much energy in our cities that we're making. I don't want to go into details of the scaling law, but the scaling law for biology is what's called sublinear. The bigger you are, the more efficiently you use energy. So if you take, you'd have to take many mice in order to make up the mass of a human. But the energy used by those many mice will be much bigger than the mass used by a human. So the scaling law is called sublinear. And this means that we can live comfortably on the photosynthetic products that's happening while we're living. So we don't have to rely on fossil fuels. Now, if you build cities, it's a superlinear scaling. And so you can't live on the products of photosynthesis while you're living. So basically you have to burn the planet in order to live. And this is the dilemma that we have. And I think looked at in this energetic way, it's a very simple energetic way of looking at the whole question of global warming. To only think of it in terms of climate change is muddying the waters, because climate change is very complicated. And it doesn't all happen at once, doesn't all happen in the same direction. It's a very complicated system. And this gives the deniers lots of excuses for saying it's all rubbish. But if you look at it purely from the thermodynamics, from the energy flows, it's absolutely obvious and undeniable that we're living unsustainably at the moment.
Interesting. Well, listen, can we go back to a bit about the sun as well?
Yes.
You know, so we sort of
It's all connected.
Yeah, let's go back to the sun. Okay, so the sun, the thing is, for this purpose, there are two types of stars. There are the very massive stars, O stars and B stars and so on, which are very blue and very hot. And there are cooler stars like the sun, and we go down to M dwarfs and so on. So the whole range of stars, and the temperature of those stars depends on how massive they are. So if we have, we're one solar mass by definition, we can go down to smaller stars, K stars and M stars and so on. They're lower mass. We go right down to about a tenth, roughly a tenth of the solar mass before we are unable to have nuclear fusion in the cores. But we can also go up the other way. We can go up to maybe 40 times, 50 times the mass of the sun, which we have around us as these OB stars, they're called. They're very bright, hot stars. They're very rare, but they're very extremely bright. And in the early universe, we could go up to 100 solar masses or so.
wow.
So, and this, if you plot these stars on what's called in astronomy the Hertzsprung-Russell diagram or the color magnitude diagram, you're basically plotting the luminosity, the brightness of the star on the y-axis, and the mass of the star on the x-axis, and that forms what we call a main sequence. So stars of low mass fall down here. Well, let's put it this way around. Doesn't matter. These are the low mass stars. They're very dim, and the high mass stars are very bright. So there's a sequence. It's not necessary, it depends how you plot it, but it's not necessarily a straight line, but it's a well-defined sequence. And you see that on all these astronomical diagrams called the Hertzsprung-Russell diagram. They're normally plotted as magnitude versus color, but it's essentially energy production rate against mass. So there's a change in the way that the stellar atmospheres work somewhere in the middle of this diagram, just above the temperature of the sun. If you're in a very hot star, all the hydrogen in the atmosphere is ionized. So you get free protons and you get free electrons. And that produces its own character of mistiness. You get mistiness from scattering of light from electron to electron. And that's quite a powerful scattering process. When you get to a temperature like the sun's atmosphere is not hot enough to ionize hydrogen. And so the hydrogen atom is generally neutral. But you still get plenty of electrons because you get that from ionizing the heavier elements, the metals in particular, sodium, magnesium, silicon, and so on. You can ionize those metals quite easily. So we in the sun have an atmosphere of basically mostly neutral hydrogen, but lots of electrons coming from the metals. And there's a very particular property of the simple hydrogen atom. You have one proton and one electron going around it, and the positive charge of that proton is not very well shielded from its environment by the single electron. The single electron's going all over the place, but it can't shield that proton, the electric field from the proton very effectively. So if another electron comes up, it can attach itself to the hydrogen atom and make what's called a hydrogen negative ion. And this is extremely important for the atmosphere of the sun. It's called the H minus ion. It's just astronomical language. It would be called something different in chemistry, and it'd be called the anion, the hydrogen anion in chemistry, I guess, and something else in biology. But this this negative hydrogen ion, this H minus, is responsible for the mistiness of the solar atmosphere in the visible and near infrared part of the spectrum. So it determines how deep you have to look into the atmosphere to see the effective surface of the sun. And in the visible part of the spectrum, where you can easily knock this electron off, the hydrogen ion, because the photons have more energy than 3/4 of an electron volt, which is what's called the dissociation energy of the hydrogen ion. If you fire a photon at it with an energy of more than 0.75 electron volts, it will ionize it. I.e., it won't ionize. It will dissociate the ion. And that's what produces the opacity in the visible part of the spectrum. So we only look so deep in the visible part of the spectrum, and that principally determines what we call the effective temperature of the sun, which is the black body that fits best the overall energy distribution coming from the sun. But if you go to 0.75 electron volts, where you lose the opacity from the H minus ion, the opacity suddenly drops to a much lower level, and you look deeper into the solar atmosphere. And because of the structure of the atmosphere, the temperature is higher. The deeper you go into the atmosphere, the higher the temperature. And so in the infrared, at around 1.6 microns, you're reaching the minimum in the solar opacity, and you're looking deeper into the star. So you get an excess of energy around that wavelength coming out of the sun. And I showed that in the diagram in the talk, where you get the Planck function, which is the thermal emission from what we call a black body, a perfect emitter. The sun is not quite a perfect emitter. It's not quite a Planck function, but it's pretty close. And there's this big sort of mountain-like peak at 1.6 microns, which is where you're looking deeper into the atmosphere of the sun. And what triggered my interest in this, and I think has not been seen by the biologists, because they don't know about this H minus ion in the solar atmosphere. Why would they? And we're taught it in first year astrophysics, but if you don't do first year astrophysics, you don't know anything about it. Anyway, this peak in the spectrum coincides almost exactly with the energy, a special kind of energy in all of life, which is called the activation energy. And it's the energy which is pertinent to this metabolic theory of scaling, which is talked about by West and so on. And what it is, if you have a bag of chemicals at a certain temperature, and the temperature is high enough that these chemicals can react with one another, all the chemicals would just react with one another, higgledy-piggledy, and they'll all end up at the lowest energy state. Now, in our bodies, we've got a complex system of homeostasis, all these chemical and physical chemical reactions going on to keep us alive. And it takes energy to drive that system. And it turns out that there's an energy which delimits the separation between you just getting chemical reactions going on higgledy-piggledy and a state where you can actually control where and when which chemical reactions happen. And so this is represented by an activation energy. And this is has the energy corresponds to quite a high temperature, much higher than our body temperature. And it's this activation energy which is the barrier that the process of life has to overcome in order to perform any chemical reactions. In order to get the electron from your food down the electron transport chain in the mitochondria and produce the ATP, the energy, the chemical energy that drives your cells, you have to control the way the electrons go down that electron transport chain. And you control that by having energy barriers, which are just the right size that you can overcome them, but you don't overcome them all in an instantaneous flood. You overcome them in a controlled manner. And it turns out the activation energy, which has been determined by biologists over all life forms from bacteria to the blue whale, the average activation energy is around 0.7 electron volts. And that's almost exactly the same as the peak photon flux coming from the sun. Now, when I realized this, I thought, that's not an accident.
Mm-hmm.
Life has evolved over 4 billion years to tune itself so that it has its structure. The structures that you have to maintain your homeostasis are tuned to an energy source which can allow you to overcome these barriers, but in a controlled manner.
But again, that's an incredible. Like, again, when you think about it, it is so obvious that life would have formed under the sun and would have, but it's so, what isn't obvious and what nobody seemed to kind of have connected until, you and a few others very recently, is that absolute connection between
it's remarkable.
And that, I guess the importance of that is, so when you say we're killing ourselves by being indoors, you're not figuratively saying it, you're literally saying it, because we need the sunlight to trigger these things, for us to live life. And if we're not getting those signals, then things are going to go awry very quickly.
Yeah, I'm not stabbing you in the back and killing you instantly.
No,
we're making people age faster. Because you're speeding up. You're losing the ability to repair your mechanisms. You need to repair these mechanisms. You need photons of about 0.7 electron volts in order to synthesize proteins and maintain your mitochondrial health and structure, generate new mitochondria and so on. And this is what we're learning from the experiments that Glenn Jeffrey and his people are doing in London. They're showing that, if you shine this light on people, we're doing humans, we're not doing mice, we're doing humans. If you shine light on people, their mitochondria work better, they metabolize quicker, and the positive effects of that, which is an instantaneous effect to some extent, the effects of that last for much longer than you're shining the light on them. There's a long-lasting tail of this, which extends over days and weeks. And this, we believe, is the turnover time of generating new proteins and new mitochondria and so on. So there are two effects of the light. One is an almost instantaneous effect of producing ATP more quickly by allowing, I use the idea of lizards going out and basking themselves on a rock in the morning sun. The biologists would say they go out there to increase their body temperature, which is true. But what they're actually doing is tuning up their electron transport process in the mitochondria. That's what they're really doing. And we could experiment on this if we could experiment on lizards, which we can't. But, you could demonstrate this with biological experiments.
And this is already reaching complete mainstream with people like Huberman and all these folks like talking about how important it is to receive morning sun. And at the same time, I'm just questioning, I'm still like having these conversations with random people about sunscreen and how they tell me that it's so important to not make your skin age. I stopped using sunscreen, I think 7 years ago. I even had skin cancer like 11 years ago. And my skin is not aging. And what you say is also saying like it helps us to stop aging. So how is that? How is it possible that people still believe that sunscreen stops their skin from aging? And do you have enough knowledge in this regards? Like, we don't want to get you off your astrophysics track, but
This is a very emotive subject.
Yeah,
Scott Zimmerman.
I know, yeah.
Talk to Scott Zimmerman about this because he's worked much more. I mean, I know what the problem is, but I really don't want to go there because I don't want to make too many enemies. But sunscreen, in my view, is essentially useless.
Yeah.
It's doing the wrong things. But that's my personal opinion. But I'd rather talk about the
We
sun.
can handle the enemies. Fine.
No, well, let's leave the sunscreen discussion to Scott.
Yeah, but I think this coincidence between the peak emission, and I had terrible trouble explaining to people, especially lighting engineers, that everybody thinks the sun peaks in the visible because all the plots you see of sunlight are watts per square meter per nanometer per unit wavelength, and they of course peak in the visible spectrum and they drop down in the infrared. Well, that's true, but the solar spectrum is not an XY plot; it's a histogram. Okay, so you bin something, you bin the energy within a small range of wavelengths, or you bin the energy within you bin the amount of energy within a small range of energy, or you bin the number of photons in a bin at a given energy. So there are many ways of representing sunlight, and they don't all look the same. And the one that's most appropriate for biophysics, what we're talking about, and also solar panels, the people who work on solar panels, is not to use watts per square meter per nanometer, but to use photon flux, the number of photons per second, per square meter, per unit area, per unit energy. And if you actually make that conversion, which I do, and astronomers do this kind of thing all the time, I do, I'm not believed, but I'm being accused of, consciously misleading people by distorting the solar spectrum to something which is completely unreal. But it's simply a transformation of a histogram, which is a little bit more complicated than transforming a point plot, because you have to take account of the width of the histogram and what you mean by the width of a histogram and so on. But anyway, when you replot the solar spectrum against a photon number, photon flux against energy, it actually peaks in the near infrared at 1.6 microns. And it's rather low in the visible, where all the photosynthesis happens. It's just the photosynthesis photons are much more energetic.
Mm-hmm.
So we're dealing with 0.7 eV photons. Photosynthesis is dealing with 2.5 EV photons. So there's a difference in the photon energy, but the biology is done with photons. It's done by a photon moving an electron or something. So once you've reshaped the way you look at the solar spectrum, you can see this peak at 1.6 microns, which is the energy you need to feed into biology to speed it up, basically to speed it up and make it run better. It's almost like a lubricant. It's like squirting oil into the mitochondria. All the infrastructure is there. It can work. It works in complete darkness. But in complete darkness, it works very slowly. And this is why animals that live in complete darkness, they can survive, but they can't do very much. And they live a very long time. This salamander that's, I don't know how long it is, but it's a little animal, lives in caves all its life. It lives for 100 years. And something that size should only live for 2 years or something.
Isn't the Greenland shark or something, which it can go up to 400 years old, but
yeah,
in the depths of the ocean.
Yeah. I mean, the deviations from these scaling laws are an incredible source of interest because they show you the weird environments, niches in which these animals live. So, although it's a very well-defined scaling law, there are deviations from it. And the deviating animals are quite interesting. The octopus, the bat, the pterosaur, which is one of my favorites.
Yeah.
And so on, all these things have very peculiar characteristics, but they all fit in this scaling picture because they all have strong deviations for their metabolism. So we've established that the sun, because it's the temperature that the sun is, has this atmosphere which is dominated by this H minus ion, which causes this excess energy. The peak would still be at around the same wavelength, even without the H minus ion. But the H minus ion means you get maybe 20% more energy at these wavelengths than you would otherwise. And it's interesting the way life seems to have honed in on this excess energy to make everything as optimum as you possibly can. So I think that's I think that's an important conclusion. I mean, I think it's something that changes the landscape.
It's really interesting. I had a question about, so we're being hit by photons the whole time, different, and there's different wavelengths. So are we as well as photons from the sun? Are we being hit by photons from other stars? And I was just kind of curious about what our bodies are being sort of bombarded with on a daily basis.
Yeah, they are. I mean, they're a very broad spectrum, yes, and not all exactly sun-like spectrum. So, yeah, but that's okay. I mean, the sun is by far the brightest source we see, so that's where all the energy transfer happens.
Right.
But the other photons can trigger different things, and I think there are other things I could tell you, but an eggshell, a hen's eggshell is, can be brown, okay? You know that. And
Yes.
And it's actually not brown. It's flecks of purple, which make it look brown. If you look at it with a magnifying glass, you'll find it's flecks of purple. And that purple is a molecule called protoporphyrin 9. And it's the precursor molecule to the synthesis of both hemoglobin and chlorophyll. In chlorophyll, you add magnesium to the porphyrin ring. And in hemoglobin, you add iron to the porphyrin ring. But this protoporphyrin 9 is a very photoactive substance, and it's used in it's not used directly, but its type of thing is used in photodynamic therapy for killing cancer tumors using red light and blue light originally. And it's a very photoactive substance. It's responsible for some types of porphyria. I think King George III.
Oh yeah, the blue wee.
suffered porphyria, and it's this protoporphyrin 9, which is I say it's very chemically active, and it can actually be transformed by light into something which is much more like chlorophyll, called a chlorine. It's very closely related to a porphyrin, but it's called a chlorine. But that absorbs at the same wavelength as chlorophyll. But anyway, the hen deposits this protoporphyrin on the egg as the egg passes through the oviduct. It sort of inkjet sprays it onto the egg, and people have wondered for a long time why would a hen do that? There was a beautiful paper by a Japanese group about 10 years ago now, where they said actually this protoporphyrin is so biologically active that it acts as an antibacterial on the shell of the egg. This is why you can keep eggs for ages and they don't get infected, because this protoporphyrin will kill most bacteria.
Wow!
In the way that it killed King George III. And so the birds, not only the hen's egg, but the birds are using this chemical as an antibacterial coat. And in other ways, and Scott and I have been discussing this for a long while now, if you look at the production of reactive oxygens in the body, which we know are damaging to life, but also important signalers in light, you can generate reactive oxygens by shining light on the skin. The skin is like a solar panel, and it will generate reactive oxygens. And, most of these reactive oxygens live a very short time before they decay. But there are things like hydrogen peroxide, which live for longer and can be derived from these reactive oxygens. And we think that the skin and sunlight is acting as a barrier against pathogens. So, we know that essentially nobody caught COVID outdoors. They all caught COVID indoors. When you're outside in the sunlight, your skin is generating an anti-pathogen coating on it because of the sunlight, which will increase the protection against viruses and so on. So, there are many photons out there that are doing things which we don't yet fully understand. That once I go beyond 2.5 microns, I have spectrometers which can measure up to 2.5 microns. Once I go beyond 2.5 microns, I'm blind, so I can't look for myself about what's going on. And it's also very hard to get cameras that work above 2.5 microns. They're becoming available now, but they're extremely expensive, and I can't afford them. So if we could look at life, between 2 and 4 or 5 microns with cameras and spectrometers in vivo, I mean, in real life, I think we'd learn a lot more. So this is something we need technology to do better. I think we'd learn a lot about the way the sunlight is interacting at longer wavelengths. When you go far enough into the infrared, you get to the stage where you're getting most of your photons from the thermal energy in your body, from your 37 degrees. And so light, then you want to get rid of light. You don't want to absorb it. But up until those wavelengths, I think the light is doing many things in our body that we don't yet fully understand. And some of it may be to do with reactive oxygen generation and other things like that. So this is why we need the full solar spectrum, getting back to the sun. This full solar spectrum is very important to us. And by cutting this off in the indoors environment, we are... You look at the rate of type 2 diabetes and obesity now, it's huge. It's huge.
I was thinking, like Bob, you mentioned windows filtering out everything but the visible light spectrum.
Yeah.
And now we learn, like week after week, we get in contact with like really interesting scientists, and they all basically agree with what you say. And then
Right.
I'm like, why don't we have windows that let all the spectrum through? And I was on X, I saw a post by a guy, and he was mentioning that he found a producer of window glass which transmits all the light spectrum, and this company is focused on animal shelters because they want to allow these animals to have like a good, healthy life. I think that's so funny, like who cares about humans?
This is a hangover from the fact from the time when we thought humans were different from animals. Yeah.
I think it's fascinating. I mean, I guess I was going to suggest we kind of conclude this bit of the podcast, but in summary, like the life, we're intrinsically part of the solar system in terms of the way, but it's also, we're not just intrinsically part, we're literally the product of the Big Bang. You can follow our history back to that, which I think is really amazing, and not something that I'd kind of particularly thought about until I saw your presentation. I think what's also really interesting is how little we know about the impact of light on our bodies, and it sort of feels like, and life. I mean, I I should say more broadly on life. I think it's very interesting, and now's not the time to discuss biophotons and things like. But the whole subject of light is just illuminating, isn't it? So I really appreciate you going into the detail around the universe, the sun, life, the scaling. I mean, the scaling thing, that's new to me this week, I guess. I really got to think about, because that to me sort of makes it sound like there's an inevitability about life based on what's kind of gone on. I think I wanted to turn now to another topic, which is in your presentation. I'm just going to mute this slightly, so I will edit this bit out. Yeah, sorry. In the presentation, we've talked about it already. You were kind of hinting at this not connection, but how the origins of stars and you know, the life cycle of stars is very similar to life. And, you know, I wondered if we could just talk about that, because, you know, life is defined by certain things like metabolism and, you know, a start point metabolism and then an end point, which, you know, it sounds very similar to, as you were sort of saying in your presentation, to stars. So anyway, I wondered if you could just talk about that in a bit more detail in terms of the way you're sort of thinking about that.
Yes, I mean, this is, I say, I've only been thinking about this for a reasonably short time, and this is that time is when all these jigsaw pieces started fitting together very quickly. So I I was sort of bowled over by this process. But you know, I say I'm certainly not the first person to point out that similarity between life and stars. In fact, you know, there is some literature, not very much literature about this, but actually part of the literature is produced by somebody I actually knew quite well in my astronomical career. He was at the Space Telescope Science Institute, and so there are discussions around this point, but I don't think they've delved very deeply into the biological implications of this. But I think there's something. If I go right back to Stephen Hawking's ideas, I mean, he in the later years of his life, he was very much concerned with, you know, the cosmology and the early universe and black holes and so on. And there is a book that was written by his student who worked with him for the last 20 years of his life, called Thomas Hertog, called The Origin of Time. It's a mind-blowing book, I must say. And the question he addresses is the whole question of the origin of the physical laws very, very early in the universe. And the idea that he seemed to be pondering was the fact that, you know, all the string theorists who are trying to calculate the values of the physical constants and understand everything from the first mathematical principles. So Hawking was hinting that it didn't actually work in that way. It worked by a process which was much closer to Darwin's ideas, in that, you know, in the very, very early universe, you know, the first 10 to the minus 31 seconds or something, there was lots and lots of energy density, and there weren't actually any physical laws then, because, you know, everything was such high temperature, such high density, and the physical laws started to emerge as the universe evolved. I'm not sure I'm explaining this terribly well.
No, you're very. It's good so far. You've
apologies
got
apologies to Stephen Hawking, whom I knew, of course, vaguely, not very well. But there was a process where certain parts of the universe evolved more quickly into complexity than others. I think this is the idea he's getting at. So there was a kind of natural selection process in the very early universe where certain kinds of physical law dominated the evolution and eventually took over. So it's essentially a Darwinian process of selecting the most effective kinds of physical behavior, called it a physical law, and become physical law, but the physical behavior of the mishmash.
So what you're saying is there could have been potentially other laws which just
yes, and the physical constants were frozen in at this point, but you know they're frozen in essentially at random because of the, you know, it's an evolutionary process rather than a mathematically driven process, and I think that means the corollary of this is that the universe we've ended up in is a universe which is good at producing complexity.
Mm-hmm.
If we weren't in if our universe didn't produce complexity, we wouldn't be here. So it's an anthropic thing in a way. But
Max, do you know Max Tegmark?
Yeah, I know. Yes.
And then in this book, Our Mathematical Universe, he describes basically how from some quantum fluctuation initial structure, an infinite amount of parallel universes was created, and we are just residing in the single one that has like all these super foundational physical constants calibrated in a way that life is even possible, and all the other universes either collapsed or blew up into nothing. And
you got the idea.
Explains a lot.
But the implications of this, of course, is the universe is pregnant with complexity, and so it's doing it as best it can. And we're only bright enough to see two kinds. One is the formation of stars and the periodic table, and the other is the formation of life. And we haven't got further yet. I mean, if I talk to ChatGPT, it'll say, "Well, I'm the next stage."
Very confident.
But you see what I mean.
Yeah.
So there is somehow we're living in a universe which wants this complexity, and that means that the physics we deal with in all these interesting things is very much non-equilibrium physics. The equilibrium physics of Newtonian science and so on is great. It gave us a good foundation. But the physics of the real world that we're living in now is a universe which is far from thermodynamic equilibrium. And it's much more like thermodynamics, the language of thermodynamics, than the language of Newton. And there are other people who are talking about this or written books about it. But I think this is the kind of picture that I have, is that, complexity is there, built in, waiting to happen. We just have to generate the conditions. And the conditions are very, very simple. And I think, as I ended my talk on the last slide, I said, well, Schrödinger would have said life is sunlight, stardust, and a cold space.
Sounds very romantic. But
that's it. That's it. All the rest is a detail in between.
Bob, I'm sure you pondered a question, and I'm taking a little departure here now. Like, what is this whole thing about? Like, do you ever think about it? And for me, this always goes towards consciousness, because that's the most fundamental, I don't know, mechanism I can think of. And also, like, when you describe how a star is working and how a star is maintaining its own entropy, I think maybe that's even like a biological or physical fact. I'm not an expert, but for me it sounds like any organism or structure that somehow maintains entropy is like alive, basically. And
I mean, I didn't say this. I mean, I thought this. Of course, I thought the star's alive. It's obvious to me, but I'm not sure I'd have the courage to say it online.
But what is not alive? I mean, for me, I've reached a point in life where I say, all matter is conscious. It's just a question on whether we are able to realize the consciousness of all matter, because some structures are just very simple. Like there's Alan Watts, this famous philosopher, and he says like a gong, like a gong where you hit on it. And like the consciousness of a gong is quite simple. It gets struck by another physical structure, then it starts to vibrate, emits a frequency, and that's basically the consciousness of the gong. And all matter is somehow that consciousness, and some organisms are more complex, like a star, as you described. This seems quite elaborate, actually. Maybe you want to touch this topic a little bit, because I'm really, really curious about it, and also given the massive knowledge you have, like, what is your stance on it?
Well, I think what I've learned, I'm very pragmatic in what I've learned, and I think, it's well known and well understood that in order to get things to happen, you have to have energy and you have to have a gradient. And I think, you naturally, in life and in the star, you get a strong entropy gradient, because you have low entropy in the center and high entropy outside, and there's a strong gradient.
It means like the amount of entropy along some axis. That's the gradient.
Yeah, and you generate entropy by utilizing energy. You're dissipating energy in the structure, and you're generating entropy. And so the presence of the energy allows you to generate a gradient of entropy. And the gradient of entropy is where things are actually happening. So if you're looking around yourself, you need to look for a gradient of entropy in order to locate those places where interesting things are going to happen, I think.
No, I mean, one thing I just wanted to turn back to complexity as well, because I had a chat with Ulysses Dormo, uh,
Yeah.
which was fascinating because he was we ended up just talking about, like, and this goes to ultra processed food
Mm,
and kind of we live in a world where convenience is, like, I think that's the overriding kind of human ambition is
mm,
convenience. And you know, I did a degree in psychology many years ago, and I remember my cognitive lecturer talking about the brain being a very lazy organ,
mm,
that it's basically looking for the line of least resistance,
mm,
it, and it kind of makes me wonder if convenience and the upshot of convenience has never been particularly good, actually. But it's sort of almost kicking back against the overriding premise of the universe
mm,
in terms of that point around
mm,
complexity. So, look, I don't. This isn't a fully, I thought, a formed idea in my head, but it's sort of. I think convenience LED lights are convenience,
mm.
processed food are convenience, like transport is convenient. All of these things have made our lives better, and yet maybe not at the end of the day.
Well, there's a word for this. It's called hormesis, and you should talk to Alastair Nunn, who was on the talk. He's the science director of the Guy Foundation.
Right.
Talk to him about hormesis. You have to stress yourself in order to remain healthy. You give yourself small doses of stress, like toxic chemicals and so on. You need to get your body to react to difficulties and build the complexity. It forces you to build the complexity, I think.
Which is really, like, I go back to, like, that whole notion of stars, like what's going on there, and again, there's an order of things which, if philosophically, if we don't sort of align ourselves to that order of things, then you know, things just probably won't work out well. So yeah, I mean, it's really, really interesting and eye-opening, like,
Mm,
thinking all of this stuff through. I mean, and ultimately, like, it, the sort of most basic thing for us, like, I guess coming out of this is re-articulating the fact that, like, we really do have this intimate connection with sunlight and the sun. And if we break that, then it's not going to end well for us, as individuals or as a species. And, there's certain things we can do about going outside and, spending time under
mm,
trees and, eating kind of like fresh fruit and all
mm,
of these things which help align us back to the natural order of things.
mm,
And again, what we're doing with Shadow Map is providing a tool so people can kind of find their place in the sun
mm,
much more easily. And I think what's great is to have, like, all of this backed by sort of deep science, and as you've managed to bridge the divide between astrophysics and biology. And I think it's so interesting that kind of that's happened. Um, so yeah, look, I wonder if you've got sort of anything else that you wanted to add. I'm very, very conscious of time because we're over
mm.
an hour and a half so far.
Yes. Well, that was inevitable, I think.
Yeah.
No, I think the main point I wanted to get over was the breadth of this topic. The whole cosmology of it, which it needs to be thought of as a cosmological issue, I think, and that results in the ubiquity of the conclusions that we draw. In fact, it applies to the whole universe. I think physics is the same everywhere, and I think the other thing, I'll end on this point, and I've used a number of aphorisms in my talk, which you can extract. But life is an antenna, with receivers tuned to sunlight.
I love that, by the way. I mean, you should be in marketing. So, you know, the other thing you said about, sorry, I've got to find the quote, and I'm going to put my glasses on. So you must sort of go into then the antennae. But you talked about, sorry, I'm going to find it. What was it? Life is, where is it?
This is the one at the beginning about the shadow.
Yeah.
Life thrives on the light that's used to form its shadow. I think
that's deep.
It is.
Very
Actually,
yes.
it is deep, I think, yes.
And then the other thing about the antennae, which, I mean, again, can you sort of just give us that quote as well? Because I think...
Yeah, I mean, the quote is, and I changed it from sunlight to starlight, but actually, you know, life is an antenna tuned with receivers tuned to starlight, and a radiator tuned to the cold of outer space.
That's so profound. Like, I mean, like you state these, like you say these quotes, and we just keep on talking. But I think we could just introduce a minute of silence so that
let people think of the implications.
Yeah.
I mean, I if you want me to end, I'll end on the thing about the shadow. The plot that I showed almost right at the end, and I have the original plot I sketched in a notebook when I was on holiday just a few weeks ago, which has this for historical purposes. When I took the metabolic theory scaling law for a fruit fly and a human, and plotted the basal metabolic rate from the literature for a fly and a human on the scaling law plot, it had exactly the slope of 3/4, as Western people say. And then I thought, I did the experiment. I just measure the cross-sectional area of a fruit fly by the area that would absorb sunlight if it was out in the sun, and do the same for a human. And I know how much radiation I'm getting from the sun within that area in this metabolically active range of around 3/4 of an electron volt. And I would just plot those 2 points on the same diagram, watts against mass. And I did that for a fruit fly and a human. And I literally had no idea where those would fall on the map. And they fell on, they fell, just to remind you, I'll show you my notebook. They fell on that line there.
Okay.
The yellow one is the sunlight, and the green one is the basal metabolic rate. So essentially exactly parallel, but a factor of 5 above. Now that means from sunlight, you have something like a factor of 5 of your basal metabolic rate available to you to spend by bringing photons into your body to allow you to thrive. Now, you're not going to absorb all those photons, and you're certainly not going to absorb all of them in the right place, but there's quite a pool of photons there. So that one plot with 2 points on it convinced me that sunlight was absolutely crucial for metabolism.
Amazing. Well, thank you so much for joining us. I mean, there's so much in there, which I need to kind of go away, think about and ponder. I think, we'll put a link into the Geoffrey West book. And it's certainly one of the ones that I'll be ordering soon. By the way, I'm trying to make my way through quantum biology by the guy, Geoffrey Guy, which I'm finding fascinating. But
yeah,
I actually tried Nick Lane's his book as well, but that was beyond me. I think Geoffrey's.
I've read all Nick Lane's books. I haven't read Geoffrey Guy's. Don't tell him I haven't read his book yet.
We'll edit this bit.
I will.
But no, look, there's so much there, and I'm sure we'll definitely be coming back to you over
Well, I think it's wise not to go on too long now because podcasts can be too long. So
I love long podcasts. I'm a huge fan.
right, okay.
Yeah,
People always complain.
But
People
it's
complain.
definitely the longest one we have ever recorded. Yeah. So
thank you.
I have
Okay.
one thing I would like before we end this. Bob, if you had one, I mean, like one main takeaway for me was that everybody basically should learn astrophysics. Like, doesn't matter what the profession, right? Do you agree?
No, I'm not saying that, but
Okay.
I think some years ago, somebody called David Christian in Britain proposed the idea of teaching in schools, not the birth dates of all the kings of the year dot, but actually teach them big history. And this is a history of the universe from the beginning right through to modern politics, but all in one subject. And he had the opportunity of explaining this idea to Bill Gates. And Bill Gates thought this was a great idea and funded the Big History Project. Look up the Big History Project on Google, and you'll find there's a huge amount of very high quality material for schools in there. And it really took off in Australia and the US, but never in Britain, I don't think.
Interesting.
Really,
Like my image for Bill Gates just recovered a little bit.
Well, yes. I mean, it was. It's terrific, and I've taught this to kids here in Bath on occasions, and they lap this stuff up.
If you would like share one thing that you would love our audience to hear, like, is there like one main message you want to share? I'm just very curious.
Well, I think it's getting outside is going to be very beneficial. I think that's what all of us would say. Glenn would say, Roger Schwelt would say, Scott would say.
Wow.
We need to fix the buildings, but that's a technical problem and it's not expensive. Well, the glass is a problem because if you use ordinary glass, you're going to fry inside a skyscraper. That's the problem. There are engineering problems that have to be solved for doing that. But changing the lighting is trivial. Well, it's not trivial, but you can do it for nothing. I mean, people ask me, how much should I pay for therapeutic lamps? And I say, between £9 and £10. And that's you getting an oven, 40-watt oven lamp that, you can still get tungsten filament lamps that go in your oven because you can't put LEDs in an oven.
Yeah.
And screw that into a little angle poised lamp.
Yeah, no.
And run it with a dimmer, run it at a lower voltage because then the filament will last forever. And you don't need it. You don't need it at full voltage. So it costs about £10.
It's amazing.
Great.
I mean, look, it's the brilliant thing about this is, there's spokespeople like yourself and Glenn and Scott and Roger. Everybody seems to be very willing to share for nothing the advice that they have. And then the cost of actually, reconnecting yourself with sunlight is virtually nothing as well. So I think it's brilliant. But thank you so much again.
Thank you, Bob.
What I just will say, my final word is that the only reason we're doing this, of course, is that we screwed up the lighting 20 years ago.
Yeah.
With the LEDs, we didn't think. If we hadn't done the LED thing, we wouldn't be discussing this now because it wouldn't be necessary, because there wouldn't be obese people, there wouldn't be people with diabetes and so on. That's my message.
Well, so you fundamentally believe that? I mean,
there are many other contributors to these diseases. I'm not saying it's everything. I think the ultra-processed food is very important, but the ultra-processed food business is very closely related to what I'm saying. It's all to do with entropy.
Yeah, no.
And it's the fact that, the ultra-processed food doesn't contain nutrients. It doesn't contain proper nutrients. You can get fat on it, but you can't thrive on it.
No, I think that's a huge difference.
Yeah.
Fantastic. Okay, well, listen, we shall leave it there, but
Okay.
It's a subject we'll probably come back to with you time and time again.
I'll try and stay alive long enough.
Thank you very much.
Please do. Get out in the sun, Bob. So
Okay, all the best. Pleasure to talk to you. Okay, cheers.
Thanks for listening to Sunlight Matters, brought to you by ShadowMap, where we explore how sunlight influences the way we build, design and live each day. If you like what you heard today, be sure to subscribe, follow and leave a review on your preferred streaming platform. You can also search Sunlight Matters on Google to find all our episodes, guest information and resources about sunlight analysis, solar exposure and the best home orientation for natural light. You can also head over to shadowmap.org, where you can download our iOS app for free today to visualize how sun is currently impacting your life. We appreciate you being part of the conversation, and we'll see you next time, where you can keep exploring the world through the lens of light.